Okay, take two, right? Yeah. Okay, rice tables are ways we're going to do calculations. In case you didn't get it the last time I said it, I'm going to say it again. Rice table stands for reaction is R, so you write out the balanced equation. I is your initial concentration. C is your change, and E is what it is at equilibrium. Okay, so the best way is to not tell you how to do it, is to show you, right? Because when I'm telling you, it doesn't make sense. Unfreeze. Okay, so here is our first problem, which our first problem actually will not require a rice table. It's just going to be a calculation. Because in this case, we have a Kp value of 0.133. Because here's why we don't have to. Because these magic words, when you see these magic words, do a happy dance because you're at equilibrium. Yeah, so when you see those magic words, these are your equilibrium concentrations, then you're not going to need to do a rice table. You'll need to do a rice table when they give you initial concentrations. Okay, so we have Kp is going to be equal to partial pressure of NO2 squared. So we don't use brackets because we're doing partial pressure. And then the partial pressure of N2O4. So plugging in, excuse me, what they gave us, 0.133 is equal to x squared over 2.71, which is what they gave us in the problem. Into 04 was found to be 2.71. So now we can do what? Math. Right? So then x squared would be equal to 0.36043, and then we square root all of that jazz, and we get x is equal to 0.600 atmosphere, which that would be equal to the partial pressure, we need to say that, of, excuse me, NO2. So because we were at equilibrium, that makes life easier. Guess what? Most of them are not going to be at equilibrium. Yeah, I promise you, you'll have to, I would be shocked if you don't have to do a rice table of some sort on the FRQ of the AP exam. Okay? You got lots of choices to choose from rice table. You can have general, you can have KSP, or you can have acid base. So they got lots of choices to give you a rice table on. Some literature will call it an ice table instead of a rice table. Guess what they left out? Yeah, you still have to do the reaction. They just figured you're going to do the reaction anyway, so they call them ice tables. So both things are the same thing. Just depends on who likes it, which way, you know, ice or rice. Okay, so in this next one, we have a certain at a certain temperature. So temperature is not important here. You have a 1 liter flask. That's going to always be important to notice what our volume is, because they're giving us moles right here. So if we're trying to find the concentrations, when we get to the end, you have to make sure you divide by volume. In this case, it's 1 liter, so it's not going to make a difference. But I want to make note of that, because if I just did it and you'll be like, oh, it's just the same thing, and then later on you give a different volume, it's not the same thing. So I wanted to make note. Circle these things. Always circle your volume so that you remember to go back and do that.
You divide by volume at the end.
At the volume, because honestly in the rice tables you need to be in moles.
Okay.
Yeah, you need to be in moles. If you'll notice this, whenever we're putting the initial and it says initial concentration, but really it's initial moles, because when we're subtracting out a reaction, we're dealing with moles. We're not dealing with concentrations, right? So it does need to be in moles. Okay, so I'm going to put up a new screen because I write too big to fit it into that space, but I think I did a good job on the notes of leaving y'all plenty of space on these. As I've been redoing the notes, I've been trying to be mindful of giving y'all enough space to write. Okay, so we're going to start with the rice table part. So we'll start with the R, which is the reaction. P, I need new styluses. And the problem tells us that we have 8, so this is the R, here comes the I, is 8.7 times 10 to the negative 3. I'm going to go ahead and write moles here just so we know we're dealing with moles. And 0.298 moles. And initially it says 0 of this. Okay? So now we're going to do our change. And because we don't know anything about the initial concentration and we don't have the K value, we're just going to assume that the forward reaction is what's happening. If we have a K value, you'll see in a minute, if we have a K value, we sometimes have to calculate a quick Q value to see which direction the equilibrium is going to lie, but they don't have a K value, so we have no way of knowing that. So we're just going to proceed. So we're going to assume that the forward reaction is happening, and we know that it's going to change by X amounts. We're going to say minus X. So however much X or reactant is disappearing, it's going to be plus X on the other side. So I like to put a line there because now we're at the equilibrium concentration. So we would have 8.7 times 10 to the negative 3 minus X, 0.298 plus X, and then X itself. But if we go back and look from the problem, it gave us the equilibrium concentration of chlorine was 2 times 10 to the negative 3 moles. So therefore, that is going to be 0.0067 moles because I subtracted it. Therefore, this one is 0.3 moles, and then this one is 2 times 10 to the negative 3. Okay? So now to find K, which is what we're ultimately looking for, we need to turn those into... Huh? I'm sorry. Okay. So there I just plugged in X and got all my values. But those are moles right there, right? Okay, so those are all moles. So we need to divide by volume to be able to get that. And so what I would do to show that I'm dividing by volume, you can do it there on, if you want to, or I would literally just show it in here. I would say 0.3 moles divided by 1 liter. That's my concentration of PCl3. And then 2 times 10 to the negative 3 divided by 1 liter, and then the bottom, which I'm running out of room. So when I plug all that jazz into the calculator, I get 8.96 times 10 to the negative 2. And it doesn't ask you anything about this, but it is always a good idea to have these things in mind in case, especially on a FRQ question, in case they asked you a follow-up question, you've already put this into your mind. K is less than 1, so reactants are favored here. And I know it doesn't ask you anything about that in the problem, but it's a good thing to keep in mind. We always want to keep these things in mind, so if a follow-up question was asked, you don't have to think about it. You're like, oh yeah, reactants are favored, it's less than 1. Okay? So that's how you solve, if you have the concentrations and you solve for K. So now we're going to have the K value and we're going to determine what the equilibrium concentrations are. Yes, ma'am.
Do you always subtract the equilibrium concentration in the reactant and how is that done?
So are you talking about right here in this area? Okay, so it depends on which direction the reaction favors. So in this case, we didn't have any information, so we can't calculate. So we're assuming the forward. In the next couple of problems, we're going to check that to see which direction. Because we're giving initial concentrations, and depending on what those initial concentrations are, we could favor the reactants, or the forward, or the reverse reaction. And then that will make a difference of if we're doing plus or minus there. Okay, so that was a good question, actually. But in this case, we have no information about K. We have no information. We have a 0 concentration of of chlorine. So if we tried to figure it out, we couldn't. So we'll just assume forward. Okay. All right. So that's going to bring us to the next problem, which is exercise 10, which I'm going to give myself another blank page. But before I do that, let's pay attention to what we know. We got another 1 liter. We got 1 mole of everything and a 1 liter flask. So yay us. Also, they gave us the K value. K, you might have lost it right there because it's on the end. It's 5.10. Okay?
Miss Parker,
Si-
whenever they say K is below a certain number, do you just use that number?
What do you mean K is below a certain number?
I don't know, on the worksheet it said K is below a certain number, like the equilibrium constant is below.
Oh.
Instead of,
Can I get through the notes and then let me look at that?
okay,
Okay, because without me reading it and stopping and seeing what it's asking, I can't answer that. Because when you read something to me, I hear blah 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 blah. I have to see it. I'm not an auditory learner at all. I'm definitely a visual learner. Okay, so new page. Delete all that. Okay. Yes.
Does the temperature affect anything on what we're doing? Yes.
Yes. But we'll do that at the end of the lesson when we get to Le Chatelier. It'll talk about temperature.
Okay.
But I'll just in a nutshell, temperature is the only thing that's going to affect big K. And little k for kinetics too. Yeah. Okay. So first of all, we're going to start with our reaction. So we have CO. I need new styluses. Plus H2O equilibrium with CO2 and H2. It gave us a... This happened earlier. It's like I get too close to the edge and it goes crazy. And I'm not even that close. Okay, K is equal to 5.10. CO plus H2O it gave us 1 mole of everything, right? And when you're setting these up, you don't actually have to write the 1 mole. I just like to do that right now, especially so you're aware of that. So because we have a K value, and because we have initial concentrations of all of our reactants, we need to calculate Q and compare it to see which way is this equilibrium going to lie, forward or reverse. So it's actually really easy at this point because we're at 1 mole of everything and we have 1 liter of everything. So what is everything's concentration? 1. So Q is 1. I don't even have to plug that in, right? Everything that goes in there is 1, so it's 1. So that means that K is greater than Q, so it's going to be the forward reaction that's favored. So what that means for our change is we're going to do minus X, plus X, and plus X. Now, if we had favored the other way, that would be exactly opposite. Yes?
even though K is greater than 1, it's still favored to the right?
When K is greater than 1, it's always favored to the right.
Oh, okay.
Okay, but that's at equilibrium. Okay, that means what that means when we see products are favored, that means at equilibrium there should be more concentration of products than there are reactants. But because the concentrations that they gave us are initial,
Okay.
we have to calculate which direction are we going. Because if we had had really large initial concentrations, we could actually have to shift the other way to reach equilibrium.
Okay.
Okay? So now we're going to do our equilibrium concentrations, which is 1 minus X, 1 minus X, 1 plus X, 1 plus X. So now we have K is equal to 1 plus X, 1, oh, that should be brackets, sorry. Over 1 minus X. And to make my life easier, that means I had a 5.10 is equal to 1 plus X squared and 1 minus X squared. Do you agree with that math? I hope so. So now what we want to do, next step, take the square root of everything to make life easier. We like to make life easier. So then that becomes 2.26 equals 1 plus X and 1 minus X. Now, I'm not going to insult your intelligence. You know how to do the math at this point, correct? Yeah. Solve for X. So I'm just going to tell you what x is, because I'm assuming you know how to do the math. Cross multiply, collect your terms, blah, blah, blah. So x ends up being, I'm just doing this so I can see what we're doing. X ends up being 0.387. So here's how we finish out this problem. We're going to say this. We're going to say the concentration of CO is equal to the concentration of H2O, which is 1 minus 0.387 over 1 liter, which is 0.613 molar. You with me? And then I can do the same thing for the other one, because there's same coefficients. This is why I can do this. CO2 concentration is equal to H2 concentration, which is equal to 1 plus 0.387 over 1 liter, which is 1.387 molar. When you are solving for x, please, or whenever you're doing this, please show which is the concentration. Like, show the brackets and say this concentration is equal to this. If they're the same, it's perfectly legal to do it just like I did it, to save some time and not having to show the math twice. Okay? But don't just say x is this and then think you're done. You got to plug it back in and show. And you've got to show that you're dividing by the volume. If it's 1 liter, great. The less mistakes you can make. But if you don't get in that habit of dividing by 1 and it shows up that it's a 1.5, you're going to miss it because you got out of the habit of just putting the 1. I know we're so used to saying, oh, it's 1, so it's this. Okay? But be in the habit of going ahead and showing it. Okay? Any questions so far? It's a lot of math. I know. I try to change colors when I do because it's a lot up there. I have a hard time writing small, especially on this, so I apologize. Okay? So now we're going to do the next one. We're working lots of problems today. In this one, we have, that's the same one, isn't it? Yeah, go to the next one, sorry. In this one, we have, here's our K value. So K is 115, because that's easier for me to work with than 1.15 times 10 to the 2, positive 2. We have 3 moles of each, okay, was added to we're in a 1.5 liter flask here. Okay, so that's going to be important at the end. Okay, so these are things that we're just going to notice before we ever go do the problem. Okay, so we are going to, also while we're at it, before I go start working it on the paper, let's calculate Q real quick. Okay. So if I have the equation H2 plus F2 yields 2HF, and I got 3, 3, and 3, right? So for Q, I'm going to have, because of that 2, I'm going to have HF squared, right? And then I'm going to have H2 F2. I'm just showing you this because this is what I would do in this problem. I would just real quickly go 3 squared over 3 squared is 1, because everything's 3. This is squared because of that 2. This is squared because 3 times 3 is the same thing as 3 squared, which is 1. So K greater than Q, so we're lying in that direction. So these are all things that I would jot up there, you know, over to the side to show.
You don't use the volume in solving for Q?
I don't use the, not in this case, because in this case, if I divide, it's going to be the same, because if I take 3 divided by 1.5, it's essentially going to be the same thing. Again, it's going to be 1.
So would you ever have to use it?
I will at the end, yeah, because at the end, I'm actually solving for the concentration, not Q.
Yeah, I meant like when you're solving for Q, you don't really ever have to use the volume.
Not in this case, no. I mean, because if I had done that, what's 3 divided by 1.5?
2.
Okay. So then it's all over. It's still squared and squared, so it's the same thing. Now, if these numbers are different in here, if they weren't all the same 3s, then I would probably need to, but cut the corners when you can, because time is your enemy on the test. Yeah.
Should that be a double arrow in the reaction?
It should be, I'm bad about not putting double arrows. There it is. Double arrow. Okay, so I'm going to erase this and do a new page because I can't fit it all on one page. Okay, so clear, there we go, whiteboard. Okay, so we have our R, which is H2 plus F2 double double to HF. So our initial is 3, 3, and 3, remembering that those are moles. Our change is minus x, because we found it lies in the forward, minus x, and plus 2x. There you go. And then our equilibrium, you don't have to do the line. I just like it. Makes me feel better. 3 minus x, 3 minus x. Again, I'm writing too big. 3 plus 2x.
And it's 2 because of the coefficient.
It's 2x because of the coefficient. Because going back to kinetics, HF is going to appear twice as fast as H2 disappears, or as F2 disappears. Remember that? Yeah. Okay. So now we can plug it into our equilibrium expression. So we have 115 is equal to 3 plus 2x squared because of the coefficient. And then on the bottom, we have 3 minus x times 3 minus x, or we could call that 3 minus x squared, right? And then our math becomes easier because it's a square, so take the square root of all of that. So then I get 10.7 is equal to 3 plus 2x over 3 minus x. And on this one, I actually wrote out all the collected things and all that. So if you want me to do that, I can.
Could you?
I could. So then I get 32.1 minus 10.7x equals 3 plus 2x. Collecting my terms, which means subtracting and adding. You know all that, right? Gives me 29.1 equals 12.7x. So x is equal to 2.29. So now that we have our x values, we can find our concentrations. Again, we can do it this way. Let's see. Let's go with red. So we can do it this way again. H2 concentration is equal to F2 concentration, which I'm running out of room, is going to be equal to 3 minus 2.9. I said it wrong, but I wrote it right, correct?
Yes.
Yeah, okay. Usually it's the opposite. I say it right and write it wrong. So, I think I have number dyslexia. I don't know. I do it a lot. Is that a thing?
Yeah.
I have it. And then, so that is equal to 0.472 molar. And now let's do our HF. So that is going to be 3 plus 2 times 2.29 over 1.5. Can't forget about the 2. 5.056 molar. I'm going to square those. Normally I tell y'all not to square them, but that way y'all can see them. Okay.
So when we say concentration of hydrogen gas equals chlorine gas, it's because of the 3 mole.
Right, it's because they both are 3 moles. If later on you'll see one, if they're not both the same, then you can't do it that way. You have to do them individually.
Okay.
But when they're the same, there's no reason to show the work twice.
Okay.
Yeah, but that's why.
Okay.
And because they both have the same coefficient. Like if this had been like a coefficient here, here on the fluorine, then you couldn't do it that way. You'd have to do them individually. Okay?
Thank you.
Any questions at this point before we do another one?
Wait.
Do you have a question, Neelish?
No.
Oh, I heard you say wait.
Sorry, no, I
Oh,
was just
wait,
thinking.
not yet. We're just signing.
Okay, one more, and then we're going to do Le Chatelier. Yeah, I was able to fit it in today, so then I'm going to give you all your work tomorrow, and y'all can do some work in class. And then I want to go over the kinetics test tomorrow. So that takes some time as well. And then we have a quiz on Thursday, and then we start KSP on Friday. Your next test is on 2 weeks from today. Okay? And it's a one-day test. Okay, last one we're going to work, and that is this one. And here we have our K value is right here. So that's 100. Okay. Are we in, we're in a 5-liter flask this time, aren't we? Oh, it doesn't matter. Why doesn't it matter? Pressure. So we're in pressure, so it doesn't matter. We don't care about the volume in this case. So we're going to calculate a Q real quick so we can see which direction we're lying. And so we would have 0.5 squared over 0.01 and 0.005. So that comes out to 5,000. So Q is less than, or K is less than Q. So we're going to shift this way. So our reaction with these pressures it's going to favor the reactants. So what that means is when we do our Rice table, we're going to do our pluses and minuses on opposite sides because we know that it's favored. Okay. So y'all with me so far while we did that? And now you know we're going the opposite direction. Okay. So clear that. New slide. So then we have our R is H2 plus I2 is 2HI. But because we calculated that Q, we're going to do it opposite. So we got 0.01, 0.005, and 0.5. So now we're going to have plus X on this side, and minus 2X over here. And so at equilibrium, we have 0.01 plus X, 0.005 plus X, and 0.5 minus 2X. So let's plug that into our equilibrium expression. So we have 100 is equal to 0.5 minus 2x squared. Notice I'm not using brackets because we're pressures. Well, this one stinks because we can't square root that puppy, can we? So, do your math, multiply, and collect your terms. I'm going to give you a hint. We're going to need the quadratic equation that I loaded on your calculators last week.
Yeah, it didn't work.
Well, then I will get it loaded after we finish the notes, so you'll have to trust me. I got it loaded on some people's, right?
Y'all can just use math. Y'all can just use math alpha to do equation solving.
Or you can do that. So when you do this, you get 9x squared
And then you can
plus 3.5x minus 0.245 equals 0, which is the quadratic equation. Which, after the notes, if I didn't get it loaded on your calculator, we'll do that with that little cord. If I did get it loaded on your calculator, go ahead and use it now. Go to Program, Quadratic Equation, and then it'll ask you to enter A, B, and C. Okay? Make sure when you enter C that you enter a minus, not a minus, negative 0.245.
Is this for finding the zeros?
It's finding the roots.
Can't we just do that by graphing?
Yeah.
Or no, Excuse me, Miss Parker?
Hold on one second. Okay. So it's going to give you two roots. Here's the issue. One of them is negative. Can we have a negative concentration change?
No.
No. So it's the other root. So it's the positive root. So it's going to have x is equal to, if you did it correctly, I hope you got 0.035. Yes?
Yes.
Excellent. So now we just do our thing. Okay? So now we have the pressure. I'm going to put no negative roots on here. for someone who is watching the video. So the partial pressure of hydrogen is going to be 0.01 plus 0.035. So 0.045 atmosphere. Partial pressure of iodine, 0.005 plus point. And I know this seems tedious, but you better show it, or they won't give you credit. Show what you're doing. And then the partial pressure of the friendly acid. Although in this case it's a gas, so it's not actually acid, it's just hydrogen iodide because it's gas. Is 0.5 minus 2 times 0.035 because of the 2x, which is 0.43 atmosphere. Okay? Any questions? Does it make sense? Okay. So then we have time to go over Le Chatelier and finish off the general equilibrium notes. We'll start KSP on Friday. Okay? So Le Chatelier is a principle, and we did this in Chem 1, so you may remember it. We actually did some little simple rice tables in Chem 1 if you're a junior. If you're a senior, we didn't. Do y'all remember them?
Yes.
Yes. Vaguely, so it seems, yeah. Now, we didn't do quadratic equation kind. We only did the kinds that you could square root to get the answer, because I'm not evil. Maybe a little bit, but not really evil. I'm just a little evil. Okay? So Le Chatelier basically states this. A system at equilibrium, which is dynamic equilibrium, will adjust to relieve any stress that's applied to the system and reestablish equilibrium. So, for instance, if I had equilibrium established and I add some more reactants to it, it's going to shift and reestablish that equilibrium. Okay? And so how it shifts is what we're going to be looking at. So if I change, okay, so these are the fancy official words of what happens. These are the fancy official words, like if you looked it up in the book or online or whatever. But I'm going to tell you the easiest way to do it is whatever you're adding, it's going to shift away from it. Okay? So if I'm adding reactants, it's going to shift away from the reactants and form more products. If I add concentration of the products, it's going to shift away from that and it'll shift back towards the reactants. So whatever you're adding, it shifts away from that. Okay? If I remove something, it shifts toward what I removed from it, which is an easier thing to say than all that words, but that's official. Like, I don't want to not tell you the official version, but unofficially, it's not unofficially, it's just in a nutshell, that's what happens. Okay? A change in concentration will not affect your overall value for K, because what happens is it shifts and reestablishes that equilibrium. Okay? So here is an example. If I had the reaction of A plus B yields C and D, if I add A or B, it's going to shift to the right away from what I added. If I remove A or B, it's going to shift toward what I removed. Okay? Same concept for the products. If I add C or D, it's going to shift away from what I added and go back towards the reactants. And then if I remove C or D, it's going to shift toward what I removed and would make more C and D. So whenever you see that arrow, that means, like for adding A and B, it shifts. So that means I'm going to start making more C and D. So those concentrations would increase because I'm shifting over there. Okay? So in the example, that is the Haber process for the formation of ammonia. If I add in 2, what's going to happen? It's going to shift to the right. Right? If I add NH3, what's going to happen? Shift to the left. If I add H2, shift to the right. And if I remove NH3, shift to the right. Okay? So that's how we deal with concentration. What about temperature? Again, whole bunch of fancy words there, the official version, but the easiest way to handle temperature is to treat heat as a reactant or a product depending upon whether it is exothermic or endothermic. And then you treat it like the concentration. In other words, if heat is a product and I add heat to the equation, it's going to shift away from heat and go back towards the reactants. if heat is a reactant and I add heat, it's going to shift away from the heat and shift towards the product. Okay? So instead of trying to remember, oh, if it's exothermic, I do this. If it's endothermic, I do that. Just treat it as a product or reactant. So then you have to know, if it's exothermic, where do we put heat? As a product. Okay? If it's endothermic, where do I put heat? As a reactant. And then treat it kind of like concentration. Like if I'm adding something to it, it's going to shift away from it. If I'm removing something, it's going to shift towards it. And then it becomes a lot easier to remember, oh, yeah, so, okay. Changes in temperature will affect K. What about changes in pressure? Okay, again, the easy version is if I increase the pressure, it's going to shift to the side with fewer moles of gas. If I decrease the pressure, it's going to shift to the side with more moles of gas. If I have the same moles of gas on each side, it's no shift. All right? Adding an inert gas, what's another name for inert gases? Noble gases has no effect because the partial pressure is not affected. Changes in pressure also do not affect the value of K. Now, one of the things that they're not putting in here that they might ask you about is, what if I change the volume? If I've got some gases, what happens if I'm changing the volume? If I increase my volume, what did I do to my pressure? It decreased. So then you would go based on that. Okay? So you're going to treat changes in volume when you're dealing with gases as changes in pressure, and remembering from the gas laws unit that they are inversely proportional. One goes up, the other one goes down, kind of thing. Okay? All right. So we're going to look at some examples. Oh, by the way, adding catalyst doesn't affect anything. It's a no shift. No shift for the catalyst. Okay. So this first equation and problem we're going to skip because it's asking about reducing volume, and then it gives us, like, this is just, that's not going to affect that one because I've got solids, liquids, and gases. So we really can only do this when you've got gases on both sides. So just, we're going to skip. Okay. So in the next one, what we want to look at is we want to look at this one. This side has 2 moles. This side has 1 mole. And I reduced my volume, so what did I do to my pressure? I increased my pressure. So on letter B, if I increase my pressure, which way is this going to shift? To the right. It's not a matter, in this case, for us, we want to remember that it's the side for fewer moles. It's not a matter of shifting products or reactants. It's a matter of shifting towards the side with fewer moles. So I don't want you to memorize it, oh, if I increase the pressure, it shifts towards the products. No, we can't do that. We got to look at where's my moles. Okay? And then in the next one, I have 4 moles and 4 moles. Right? So what's going to happen? No shift. Okay? And then last problem in the notes, but then I have something I want to talk about with Le Chatelier, and that is temperature here. We're increasing the temperature. So this is endo or exo?
Endo.
Endo. Where do we put heat?
Left.
Put heat over here. Anytime you see a problem like this, I don't care what it's asking, go ahead and do this so that you don't screw it up. Because they may or may not be asking about this, but if you're keeping this in mind all the time, then you don't mess up. This is exo, so heat goes over here. So if I increase the temperature in the first one, what happens?
Shift to the right.
Shifts to the right, because I shift away from my heat. And then in the next one, I am increasing my temperature, so it shifts to the opposite direction because I shift away from my heat. Okay? So here is what I want to talk to you about Le Chatelier versus equilibrium K, calculating K. So before the redesign, you could use Le Chatelier to answer so many problems on the FRQs. And it was great, and it was awesome. And then they was like, that's not a good enough reason anymore. So Le Chatelier is like the quick, easy, dirty way to do it on a multiple choice. If they ask you a question about something, Le Chatelier it, okay, and say, oh, it's shifting because of blah, 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 okay? On FRQs, especially if they're giving you numbers, don't say, according to Le Chatelier, if I do this, blah, 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 but no, do the calculations. Always, when you can, on a FRQ, you want to compare K and Q and say it shifts according to that, okay? That's what you want to use on there. There you got to do the calculations and show them why. So a lot of those calculations we just did, you know, you wouldn't be able to use Le Chatelier, but sometimes you're tempted to do it on an FRQ, unless it's specific. Now, if they're asking about temperature, you pretty much have to use Le Chatelier to explain temperature because you have no numbers affected or whatever, okay? But for the most part, you want to quick and easy do a question about shifting with Le Chatelier on the multiple choice, but on the FRQs, we tend to have to do the calculations for comparing K and Q. All right? I'm going to stop recording unless you think this question needs to be on.
Oh, I think this question is.
Okay, what is your question?
How would K be affected on A and B for these last one?
So if you are increasing the temperature of K, so in the first case, since we are shifting to the right, will we be making more product? So K should increase because we be making, right? Think about, remember, think of the general terms of products over reactants, right? And so in the first case, if I'm shifting to the right, I'm going to start making more products, so my K value would go up. In the second case, I'm going to be increasing my reactants, so I'm going to have a bigger number on the bottom, so K would go down. And that was actually an excellent question. Thank you, Neelish. Excellent question by Neelish Gupta. Circa 2020.
Thank you.